Welcome back. And thanks for staying with us or joining us. We're ready for the next talk. And I'm very happy to welcome Mark Seaman in live in the Channel 9 TV. So hello, Mark.
Hello. How are you?
I'm pretty good. How are you?
I'm doing fine. It's Friday evening here, so what a wonderful way to spend a Friday evening here in Copenhagen. Yeah.
Yeah, we did this nasty thing to all the Europeans, where rather than spending the Friday night with their family, they have to either tune in and listen to us or join us.
Yeah.
Right. I think we are ready to switch to your talk. Just for the record, how long have you actually been playing with F#?
For about five to 6 years now. Yeah.
5 to 6 years.
Yes.
So and your background, for a change, is actually software development.
Yes. I used to do lots of C# development before I switched to F#, and I did a gradual switch. But now I would say F# is my main language.
So I think that will be really cool for lots of the people in the audience who are coming from the C# background, and they sort of want to understand how the programming is done in F#.
Right, then this is the perfect talk. I'm not really going to assume that you know anything about F#, so I'm just going to walk you through whatever's going to happen here. Still going to be fast-paced, but yeah. And even if you know F#, you probably will pick up a couple of things, I hope.
Yeah, the fact that it's fast-paced is really our fault, because we only gave you 45 minutes slot.
True.
All right, so we're ready to go. I'm going to switch over to your screen, and you're all live now.
All right. Well, thank you, everyone, for tuning in to this talk. It's called Types plus Properties equals Software. My name is Mark Seaman, as you can tell. I'm not going to bore you with the details. If you want to know more about me, you can go to blog.plur.dk, and there's an about page there. I'm also at Twitter, on Twitter at Plur, and always interested in joining any discussion if you have questions and so on. But let's get started with how to build software using types and properties. That's what this talk is about. And the first thing we need to establish is, what are we actually talking about when we are talking about these things? So we'll start to talk a little bit about properties. So you may think that you know what a property is, and particularly if you are a C# developer or maybe a Visual Basic developer, you think that you know what a property is, because this is basically a property. This is an automatically implemented property in C#. And we have those in F# as well, and in F# they look like this, and you will notice that that's actually more verbose. It looks more verbose than the C# version. And the reason for that is that we don't really use properties in F#. They exist for interop reasons. So if we need to interoperate with C#, or if we need to publish something that C# developers need to interoperate with, we can do that. But we don't use them that much. So we don't really mind that they're verbose, because we don't really write them that much. But basically what I'm trying to tell you here is that the types of properties that I'm going to talk about today is not that kind of properties at all. It's also not this kind of properties. So when I'm talking about properties here, I'm not talking about any sort of real estate or anything that you can actually own. Instead, what I'm going to talk about here is that a property in today's, what we're talking about today, is a synonym for a characteristic or a quality or a feature or whatever else. So this is kind of an overloaded term. So basically what we're trying to do here is we're trying to describe the properties of a particular system. And when I say system, you can think about systems as functions. And basically you can think about your entire application as a single function that is composed of other functions. But we're going to be a little bit lower level here today. So basically what we're trying to do is we're trying to describe the behavior of a particular system using various properties. So often if we try to describe a particular system, we would need more than one property to actually describe the behavior of a system. So by still saying, well, the system has this property that blah, 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 and it also has this property that blah, 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 and so on, what you actually end up doing is you basically end up describing or characterizing the system using various properties. So that's simply a way of describing a system. Now, what we're trying to do here is, and specifically what interests me, is something called property-based testing. And property-based testing is this idea of trying to describe the properties of a system and thereby describing the behavior of the system by properties that are executable. So a property is an executable test. And even though it's sort of abstract, the property sounds like sort of an abstract thing, it's very concrete in the sense that it's executable. So we're talking about executable tests here, just like we're talking about other types of unit tests. You can think about this as a sort of unit testing, actually. But since the properties are abstract, you may pose the question, so how do we describe something that is abstract and still make it very concrete? And the way that we do that is by using randomized input to express deterministic automated tests. So basically what we're trying to do is we're trying to say, well, we'll randomize input because that forces us to think about the description of however the executable test will behave in terms of observable input and output instead of examples. And it's important to realize here that I did underscore the word deterministic here. So even though we're using randomized input is basically just a way to seek out boundary cases and also to force ourselves to think about the overall property of a system instead of just thinking about in terms of examples. And I'll show you examples of this in a moment, though. But it's important for me to underscore here that we are still very much in the realm of unit testing. We're still very much in the realm of doing deterministic tests. So if you have a unit test suite or property-based test suite, and you run that test suite once, and then you run it again without changing anything, you will have the same results from running it the second time that you had the first time, and so on. So this is a very important characteristic when you're doing test-driven development or unit testing, and it's also something that we do when we do property-based testing. Right. So basically what we're trying to do when we do property-based testing is we try to describe a relationship between the input and the output. And one of the things that we have to deal with property-based testing is that we don't really know exactly what the input is going to be, because we're going to have some sort of random value generator that's just going to generate lots of random input. So when we don't know what the exact input is, we also don't know what the exact output should be. So if you've ever done test-driven development using concrete examples, what we call example-driven development, what you probably be used to do is to say something like, well, if the input is foo, then the output is going to be 42, and if the input is bar, then the output is going to be 1337. And sometimes, the relationship between the input and the output is not particularly clear. But you can't really do that here because you don't know what the input is, so you also don't know exactly what the output is going to be like. So what you have to do instead is you have to describe some sort of relationship between the input and the output. And I'll show you examples of how to do that. So one of the questions you might have is you might want to say, well, okay, so how do you actually do this when the input is random and unknown? One of the things you may wonder is, well, if we randomize all the input into our test cases, how do we even make sure that the input is meaningful? Will we just get, a random stream of bytes? Is that actually what's going to happen? And it's not. What we're really trying to do is even though we're trying to randomize the input into test cases, we still very much want all the randomized input values to be meaningful in the domain context that we're actually looking at the moment. So we have to somehow be able to determine or to instruct our random value generator to generate values that are both random but still meaningful. So how can we do that? And this is where the types come in. So what we can do is we can make illegal states unrepresentable. And this is a catchphrase that I've borrowed from Scott Blartin, who's going to be on later tonight, I think. And I think he borrowed it from someone else whose name escapes me at the moment. But basically, the idea about making illegal states unrepresentable is sort of like the little bit of the same thing as encapsulation when you talk about object-oriented code. But you can sort of take it to the next level with the type system that F# offers. So basically what we're trying to do, and I'll show you an example of this, is that we'll design the types that we're going to use in order to model our domain in such a way that they can only represent things that are actually meaningful. And that means that the random value generator that I'm going to use, for example, I'm going to use something called fscheck, it's not going to be able to generate values that are not meaningful because they are not representable. So basically, the idea is to design with types in such a way that illegal states are unrepresentable. And that means that half the job is almost done, in the sense that now if fscheck or another random value generator can simply just pick up on those types and start generating random values. And then we can express properties based on those random values. So it's time for an example. So basically what I'm going to do for the rest of this talk, so for the next 30 minutes or so, is to show you an example. So we'll need an example to look at, and I love this kata called the tennis kata, so that's the one that I'm going to do here today. So the tennis kata is just a simple software exercise. And basically, the idea is to try to model the scoring system for a tennis game. So a tennis match is made up of several sets that are, again, made up of several games. And we're just going to model a game of tennis, so just a small part of the overall tennis scoring system. Basically, if you can't remember how that works, it's you start out with having two players, and each player can have either love, 15, 30, or 40 points. And the goal of the game is to get beyond 40. So if you have 40 points and you win the ball after having 40 points, well, if you win the ball again and you already have 40 points, you win the game. But there are special rules. So one of the special rules is that if both players have 40 points, we don't really call that 40-40. We say that the score is deuce. And when the score is deuce, the winner of the ball, the subsequent ball, will have advantage and game ball. And if the player with advantage wins that game ball, he or she wins the game. And otherwise, if the player without advantage wins, then the score is back at deuce. So that's basically what we need to do. So the tennis kata, if you've ever tried it, you will probably appreciate that it's a very, very nice kata. If you've never tried it, you really should, because one of the things that I like about the tennis kata is that it's just difficult enough to be fun, but it's not so difficult that it's not fun. So it just has the right amount of difficulty. So it's still quite a simple problem, and you can solve it in lots of different ways. But you can think about the tennis kata here as a stand-in for a much more complicated business domain. And maybe if you do that, you can start to see some of the benefits that you can get out of using F#'s type system and property-based testing to flesh out the behavior of a system. So what I'm going to do is I'm going to switch to Visual Studio here, and as you can tell, I have a tennis module here on my on the right-hand side of the screen, and then I have some properties here on the left-hand side of the screen. And what I'm going to do is I'm going to start just writing some types in the right-hand side of the screen here, and I'm just going to design with those types in order to make illegal states unrepresentable. And then later on we'll go and write some properties as well. So the first thing I want to do is I just want to say, well, there's going to be a type called player, because what I want to do is I want to model that there's going to be player 1 and player 2. So basically what I'm trying to do here is that I try to model that there are only two players in the game. And I just hit Alt-Enter, which means that I send the types down here into F# Interactive, which is my REPL. And if I switch down to the REPL here as well, I can start typing. So for example, I can type player 1 here, and you will see that it reports back that that's an implicit value. It is an implicit value, and it reports that that implicit value is of the type player, and it has the specific value player 1. So it's actually statically typed, even though it doesn't look very typed because there's not a lot of type annotation. But basically it says, well, this value is of the type player 1, and I can also write player 2 in order to see that that's also a possible value of that player type. But on the other hand, if I try to write player 0, for example, that's not going to be possible. You can see that the compiler here simply says, well, that's not defined. And also, if I try to say player 3, that's also not going to be possible. Because that value is not defined. So already I'm a little bit on my way in order to make illegal states unrepresentable. In this case, I'm just saying, well, there's going to be those two players, and that's the two players that I'm going to have. So this may probably make you think of an enumeration, a C# enum, for example, and it looks a lot like a C# enum at the moment. But the player type is actually something called a discriminated union, which says, well, the player can have either of these two cases. In this case, there's no additional data associated with each of these cases, but we'll see more advanced examples of this later on. So that should take care of the players. And the next thing I want to do is to try to model what points look like. And you may recall that points are love, 15, 30, and 40. And the first naive attempt might be to say something like, well, we'll just say that it's an integer because, 15, 40, and so on actually sounds like integers. So we could say something like, let P, which is a point, be equal to the value of 15, for example, and we can model that, so that's fine. We can also model, for example, 40, and we'll say, okay, so how do we model love? And love is actually sort of 0, because that's this point value that each player has when the game starts. So we could say something like, well, we can just say, well, let's just imagine that it's 0. It's a little bit of a stretch. It's not quite domain-driven design now, but we can probably get by with that. But the problem is that, I can write anything else. So I can say, well, a point could be 7, or a point could be, minus 27, or all sorts of other things. So actually, even though that I've made legal states representable, I've also made lots of illegal states representable. So I haven't succeeded in making illegal states unrepresentable yet. So that turns out to be a really bad idea. But what I'm trying to get across here is, a very common way of working with F# code and designing with types is that you try to define some types here in your module, and then you send them to F# interactive, and then you play around with them a little bit just to try to understand what can you express and what can't you express. And sometimes then you go back and say, well, okay, that didn't work out. Let me try something else. And that's what I'm going to do now. So fairly if you've done this a couple of times, you probably realize then that, even though those values, love, 15, 30, and 40, even though they sound like integers, they're actually not. They're more like labels. So I can just model those as a discriminant union as well. And that means now I can, for example, write love, and that's fine. And I can write 40, for example, and that's also fine. But I can't write, if I want to write 3, for example, that's not possible because there's no value called 3. So that actually brings me a little bit closer to my goal of making illegal states unrepresentable, because now I can only refer to a point with one of those 4 labels. And it's going to be fine with those labels because I'm not really going to need to do any arithmetic on those values anyway. I'm not going to need to add or subtract or multiply them with anything anyway. So that's actually going to be fine. But a point is not really a score. It's just part of a score. A score is something where one player has a particular point value and another player has a particular point value. So I'm going to define a new type called points data, and this time I'm not going to define a discriminant union. Instead, I'm going to define something called a record type. So I'm going to say, well, player 1 point is going to be of the type point, and there's also going to be a player 2 point, which is also going to be of the type point. All right, so that's not really all of it visible. So let's just do this point. There we go. Right, so I can try to send this to F# interactive again, and I can play around with that a little bit. So I can say something like, okay, so player 1 point is equal to love, and player 2 point is also going to be equal to love. And as you can tell here, the compiler simply infers that this must be a value of the type points data, because that's the only type that's currently in scope that has player 1 point and player 2 point named elements. So it's unambiguously a points data value. So it's very strongly typed, even though you don't really see any type annotation in the expression itself. So I can write something like love 30, for example. That's another value, and I can write love 40. That's fine. Those are all valid values. I can also write 4040. And this is where problems start to appear again, because 4040 is actually not a legal value. The legal value, when you hit something that ought to be, that could be 4040, is deuce. And then you might argue, well, okay, but couldn't we just sort of imagine that 4040 is deuce? Couldn't we just, internally model it as 4040 and then call it deuce when we talk to the external world? And you definitely can do that, but it just turns out that the code actually doesn't become simpler if you do that. The only thing that you actually end up doing is that you disconnect the code implementation that you have from the domain language. The domain language is the language of tennis. So if you're into domain-driven design, you probably say, well, if the domain experts call this deuce, we ought to model this as deuce as well. And also deuce is subtly different from 40-40, because what might happen if you start with 30-40 and then player one wins the ball, so now you're at 40-40, or you're at deuce, and then player one wins the ball again, then you have advantage to player one, and then player two wins the ball, now you're back at deuce. But you're not really at 40-40 anymore. So we should probably not allow ourselves to model 40-40 in this way. So this is an illegal state that is currently representable, and we don't want that to be representable. So back to the drawing board. We're zeroing in on the correct or one good model. So we don't have to start completely from scratch. But what I'm going to do is I'm simply going to remove that 40 option here. And I can send that to F# Interactive again. And that means now if I try to say 40-40, now the compiler is actually going to complain and say, well, that's not going to work because there's no such thing as 40. But I can still say something like love 30, for example. That's still a valid value. And then you would probably say, well, okay, but what about love 40? You can't say love 40 anymore. And that's completely correct. I can't say love 40 anymore. So obviously, I need to be able to model the situation where player one, for example, has love and player two has 40, but I can't express that with a points data value anymore. So the question you may have is, did I just throw the baby out with the bathwater here, or is this actually something that enables us to move forward? And luckily, we can still move forward, because I wasn't really done modeling scores at all, because I didn't really have a model for deuce and I didn't really have a model for advantage yet anyway. So I'm not done at all. So that's fine. So I can just keep moving on. So basically what I'm going to do now is I'm going to say, well, let's define another type. And in this case, I'm going to define a type called 40 data. And it's going to be another record type. And basically what I want to do here is I want to model explicitly when one of the players has 40. So in the case where one of the players has 40, what I need to keep track of, for example, is which player actually has 40 points. So I'll create a named element called player of the type player. And I also need to keep track of the other player's points, other player point. And that's just going to be a value of the type point. All right, so if I play around with 40 data for a little while here, I can say something like, well, okay, so the player is player 2, and other player point is, let's say, 30. There we have it. There's a 40 data value. And again, the compiler can just see that this must be a 40 data value, because that is unambiguously the only thing it can be. So there are various ways that I can model. In this case, I'm modeling that player 2 has 40 points, but I can also just say, well, here's a value that represents that player 1 has 40 points and the other player has 30. So that moves me a little bit closer to where I actually want to be. So at this point, I'm actually ready to define a type called score that models what a score looks like. And the score is going to be another discriminated union, but in this case, now that discriminated union is going to be more complex. It's not going to look like an enum anymore. But basically what I'm going to say is there's going to be a case or phases that a score can go through. And the first case is a case called point. And when the case is point, it has points data associated with it. But it might also go through a phase where one of the players has 40, and in that case, it has 40 data associated with it. It may also be the case that the score is deuce, and when it's deuce, it doesn't really have any other data associated with it, so I'm just going to go on to the next line. Also, it might be that the game or the score is that one of the players has advantage. So I can say advantage of player, because I need to keep track of which player actually has advantage. And finally, one of the players can win the game. So I can say a score may be game of player. So a score can be one of those 5 cases, and those are mutually exclusive, but they all belong to the same type. So I can take all of this and send to F# Interactive, and now I can try to play around with it a little bit. Again, if I take this expression from before, the compiler can see, well, this is a 40 data value. And if I scroll up here so you can see the 40 type here, or the entire score type here, you will notice that the 40 case here, it actually sort of behaves like a function, and I call this a case constructor. I may have picked that up from another language, But basically, you can think about this as a function that takes a 40 data as input and returns a score value as output. So, and the name of the function is 40. So if I take this expression that I had from before and simply call the 40 function with it, you will see now, instead of reporting that it's a 40 data as it did before, it now says, well, this is a score value. And I can do exactly the same with some of the other expressions that I had here. For example, I could say love 30, that's a points data, and I can call point with that, and you can see again now this is a score value. And the same goes if I just write deuce here, you can see that's a score value as well. Advantage to player 1 is also inferred to be a score value. And that also means I can start to compare those things to each other. So, for example, I can say, well, is advantage to player 1 equal to deuce? No, it's not. That's an equals operator. That's a comparison operator. It's not an assignment. And I could also say advantage to player 1, is that equal to advantage to player 1? Yes, that's actually true. So because it's the same type, I can compare those values, and they have structural equality. So at this point, I'm pretty much done modeling my domain, in the sense that what I have here now is a type system that models the score of tennis in such a way that illegal states are unrepresentable. And let me just demonstrate that for you as well here. So what I can say is, I can say something like, well, I can say that I have a point case like this one, where player 1 has love and player 2 has 30. But I can't, for example, say something like, well, okay, so what about player 0? That's not going to be possible, because that's not really part of the type system. Or I can't really say, well, it has 42 or whatever. So all of these things are not really possible. I can't really represent something that is not legal. So that's really nice. So designing with types here is basically always already half the battle won. But what it does here is it enables me to model valid score values, and also it disables me, or prevents me from modeling score values that are not legal. But it doesn't govern how I can transition from one score value to another one. So a legal transition might be to say, well, okay, the score starts at love, and then player 1 wins the ball, so the next score is 15 love, and so on. But I could, at the moment, I could just say, well, the game starts at 30. 40, and then the next score is going to be deuce. That's actually a correct transition. But then the next score is going to be love. Nothing prevents me from that. The type system does not prevent me from that. So I need to describe the behavior of the system as well. And that's where we can use properties. So I'm going to switch over here. I'm going to just make a little bit more room, and I'm going to move over here to my tennis properties and start adding some properties. And you can see I've already imported something called fscheck, which is the random value generator that I'm going to use. It's called it's a property-based testing library, actually. It's a port from QuickCheck that originated with Haskell. And then I have imported and opened something called fscheck.xunit, which means that xunit.net is my xunit is my unit testing host. That's actually that's the test runner that I'm going to use. And then I have something called Swenson unquote here, which I'm going to talk about in a moment. And then I've opened my tennis module as well. So the first thing I'm going to do is I'm going to write an attribute, and I'm just going to write an attribute called property. And then I'm going to write a function. I'm not going to call foo, but I'm just going to talk a little bit about it. So I'm just going to call foo temporarily. So first of all, if you're a C# developer, you probably know attributes without those angle brackets. So in C# this would be an attribute, but in F# we just need to put those angle brackets on as well, because the square brackets alone mean something else. Right. So this is just a normal attribute.net attribute as you know them, and this is just something that tells xunit that this is actually something that can provide values, basically like a theory in xunit. So the next thing is that we have here is a function, and a function at the moment, this function is called foo, and it doesn't really do anything. So these two empty brackets here is a value called unit, which basically just means nothing. So I'm not going to call the test foo, but it's just that I just wanted to show you that's actually possible. There's no restriction on names at all. But what I'm going to do is I'm going to use double backticks here, and that enables me to write test names with all sorts of I can use special characters and spaces and so on. So that's just an F# feature. What I'm going to do is I'm going to say, well, given, I'm just going to look at the advantage state because it demos pretty well. It's not too complicated, so we have time for that. So I'm going to say, given advantage, when advantaged player wins, then the score is correct. Something like that. That's what I want to do. And you'll notice that I use this given when then terminology like the Gherkin language. And the only reason I do that is just because I think that that's actually a pretty decent description of the test case that I want to do. It's not behavior-driven design or behavior-driven development. You don't get any advantage of doing given when then compared to anything else. It's not going to be a text file that you can give to your business experts or anything like that. I only named this because I thought that was actually a pretty readable test name. So it's only there for developers, just to make other developers reading this code happy. So what I'm going to do here is that here I have my argument list to the function, and right now the test function doesn't take any arguments. But what I want to do is I want to say to fscheck, give me a player value and give me the player that is the advantaged player. And so there's a little bit of a type annotation here saying, well, okay, give me a player value. It could be any player value. I know there's only 2, but you could imagine that if we could, have more values, we could just get, arbitrary player values. And then I'm going to say, well, okay, let me get the actual value, and I want the actual value to be a score value. So I'm actually doing test-driven development here. So I'm trying to drive my design and try to get feedback on the design while I'm actually driving it. So I'm going to call a function called score when advantage, and that function doesn't exist yet. And what I want to do is I want to supply to that function, this is a function that only needs to deal with the advantage case, but I want to tell it what is the current state of the game. And when you're in the advantage case, the current state of the game, the only thing you need to know about the current state of the game is which player actually does have the advantage. So I'm going to say, well, that's the current state of the game, that player has advantage. And then I also want to supply another argument to this function saying, okay, and which player actually wins the ball. And that's also going to, in this test case, that's also going to be player. So I'm passing the same player twice, and you'll notice that I don't need to know exactly the value of the player. I'm just going to pass the player whatever it is, and I know that the player can only have a valid value because I've designed it that way. So it can't be player 3 or player 0 or player -1 or whatever. It can be only player 1 or player 2. Right. So that's going to give me my actual value, and let's get the expected value as well. And I'm going to say, well, okay, so if the player already has advantage and that player wins again, the expected outcome of that is that that player wins the game. So you can see, I just say, well, okay, the expected value is game for player. So again, I don't need to know the exact value of player, but I just need to establish this relationship. And now I just need to write an assertion, so I can say something like, well, expected must equal actual. And you probably, if you haven't seen this operator before, you say, well, not equals. But this is actually not the not equals operator. If you are a C# developer, you probably know the not equals operator as this one, and this operator doesn't exist in C# at all, in F# at all. In F#, the not equals operator looks like this, but that's not what we're doing here. This operator comes from Swenson unquote up here, and I'm going to talk a little bit more about what it does in a moment, but basically you can read it as must equal. So this is an assertion. You can read it as expected must equal actual. If you've ever done NUnit or xunit.net unit testing in C#, you're probably used to writing something like assert equal expected comma actual, and that's exactly the same thing that's going on here. So this doesn't compile at the moment because score when advantage doesn't exist. Let's go and add that. I'll add that to my tennis module here. So I can say let's score when advantage, and I want to say, well, the current player is the first argument, and then there's the winner of the ball. This is the second argument, and I needed to return a score value because otherwise my test is not going to compile. But I want to see the test fail before it actually succeeds, so I'm just going to return deuce here because deuce is also a score value, so that's actually going to compile. And I can try to run the test now to see whether it fails as I expect it to do. And you can see my output window here pops up because I'm using a test runner called testdriven.net. And one of the nice things about testdriven.net is that it's very keyboard friendly. So I can just hit enter here and it takes me to that assertion that I just wrote. And I'll pop up the window again, because if we scroll up a little bit, what it actually tells me is it says, well, this test failed. And basically, falsifiable, it says here it's falsifiable. And basically what it means is this property is expected to hold for all player values. And if you can come up with a counterexample, or if fscheck can come up with a counterexample, we say that fscheck can find, it can falsify that property. So in this case, it says, well, it's falsifiable because it can come up with a counterexample. And particularly the input for that counterexample is if we provide player 1, for example, the test actually fails. And then Swenson unquote here takes over and it reports on exactly what happened. And basically what that does is it takes that Boolean looking expression here and it plugs in the actual value. So instead of just reporting on expected must equal actual, it says, well, expected was game for player 1. Because the input up here was player 1. But what I got back was deuce, because that's actually what I hard-coded into the implementation. And this Boolean expression here, so it's not an assignment, that equal sign, it's a Boolean comparison. And it says, well, is game for player 1 equal to deuce? And no, that's absolutely not the case, and that's why the test fails. So you can see unquote here actually gives you a very nice report of exactly why did the test fail. So this test is actually pretty easy to pass, because I can just go and say game for winner, and that should pass that particular test. So that's the simplest thing that can possibly work. And you can see now if I run my test, you can see, well, there's 1 passing property and there's 0 failing and 0 skipped. And you can also see the output from the property is this. It says, okay, passed 100 tests. So what actually happens is that this function here actually runs 100 times with randomly generated player values, and it passes for all those 100 in all those 100 times. And the number 100 is just the default value in fscheck. You can configure that if you need it to be a different value. So obviously, if we look at the implementation over here, it's not correct. So we'll need to add another property. So I'm going to do that. All right, so I'm going to say, all right, so again, given advantage. So I'm going to start with the same thing, but when other player wins, then score is correct. All right. And again, I'm just going to ask for a player value. And I think I can almost get rid of the type annotation here. So I'm going to say, again, my actual value should be calling score when advantage. And again, the current state of the game is that player has the advantage. I think I even don't need those. But then I want the other player to win the ball. All right, so other doesn't exist yet. So if we move on here, you will see it actually gets red squiggly lines under other because that function doesn't exist. I'll add that in a moment. But basically what we can say is, okay, if player has the advantage, but then the other player wins the ball, the expected outcome of that is deuce, and that must equal actual. All right, so that's the test that I want to write. So other should be a function that gives me the other player. So I'm just going to go over here. This is actually a pretty generally useful function. So I'm just going to actually add it to the tennis module. I'm going to say, well, that's going to be a function that, when player 1 is the input, it's going to return player 2. Let me write this so you can actually read what's going on. So let's say something like, let's break it up here a little bit. So, and if the input is player 2, it's going to return player 1. All right. Right, so this is just a function that returns the other player, hence the name, other. And you may say, well, shouldn't we test that as well? And we could, but it's quite simple. So I'm not sure that that's actually going to give us any advantage. So for now, I'm just going to let it be here. So I'm going to start testing again, and you can see that it pops up. And if I hit enter, I'm taking to that new assertion that I just wrote, so that's good. That's what I hoped would happen. And again, we can see it's falsifiable. For example, if the input is player 1, it expected deuce, but it got game for player 2 back. And that's actually not what we want. So Right. So what we need to do is we need to go over here to the implementation, and we say, all right, so if current is equal to winner, then it's game for that winner, else it's deuce. Right, and that compiles, and we can run the test. And you can see now I have 2 passing properties and 0 failing, and each of them passes 100 tests. So that's pretty good. So you can pretty much just keep on going like this. But I don't really have time for that. So what I'm going to do here is I'm just going to fast forward. I have everything here in a Git repository. So I'm just going to reset this one, and then I'm going to check out master. And you can get this. This is on GitHub, and I'll show you a link in a moment. But I'm just going to go back here and reload everything. And you'll see that it added some more code here as well. But I'm just going to run all the properties. And you'll see what I actually ended up with is some, let's see how many did it actually do. It ended up, I ended up writing 24 properties. So you can see it passes 24 properties. And some of the ones that I wrote ended up writing was as a little bit, they're a little bit superfluous, if you will. But I just wrote them to demonstrate that you can do various things. So all of this is available, and I'll show you a link in a moment. So basically what I ended up doing was I wrote a function that corresponds to each of those cases in score. So you just saw the you just saw me write that score when advantage function here, but also I wrote a score when game, score when deuce, and so on. And then I ended up writing a function called score here with a lowercase s, and it takes a current score as input, and the player that wins the ball, and then it returns a new score as output. And basically, you can see it matches on current. And for example, if the current is an advantage case, it calls that score when advantage function that you just saw. And I also defined a value called new game, which is basically just the value where each of the players has love points. So if we take all of this and just send that to F# Interactive, what I can do now is I can look at some examples of how you would use that. So for example, I can say, well, okay, I can call the score function here with that new game value, and I can say player 2 won the ball. So if I send that to F# Interactive, you can see first ball is a value where player 1 point is love and player 2 point is 15. And now then I can use first ball as an input to score again, because that's a score value as well. And I can say, well, player 1 wins the next ball. And and now I get second ball is also score value, and that is 15-15. But you also pretty soon get tired of doing that. So what you can do instead is, if I scroll down here, you can say, all right, well, what you can actually do is you can do something called a fold, which is basically like an aggregate. And you can say, well, you can call, if the input is a sequence of players, I'll show you an example of this in a moment, you can just do an aggregate where you keep on folding over that score function. And the initial state of that operation is that new game, and then you can just pass in those wins. So I'll show you an example of that. So here I have a list of player values, and basically the idea here is to say, well, all right, so this is a representation of a game, and that means player 2 won the first ball, also won the second ball, then player 1 won the third ball, and player 2 won the fourth ball, and so on. So that's just a list, and I can call that score seek function with that. And you can see now that the simple game value then evaluates all of that to say, well, the final score is that it's game for player 2. Right, so I think it's time to wrap up here. So basically, if you thought this was interesting, well, there's plenty of information there on blog.plur.dk. Also, I have lots of courses on Pluralsight, and I just created this little joke link bit.ly/Pluralsight, because I'm Plur, and Pluralsight, yeah. So that's just a link to all my Pluralsight videos, and I have one on property-based testing and one on other types of testing with F#, and also some C# things. And I also just want to show you, if you thought this code example was interesting, I wrote a series of blog posts about that, also called Types plus Properties equals Software. It's there on blog.plur.dk. And this is just an overview article, and you can scroll down and you can see there's all sorts of various articles for that as well. And if you click one of them, you can see, you can read lots about what I just showed you, and you can click on the available on GitHub. Link there, and then you can see the entire repository that I just showed you here is actually available on GitHub. So that's what I had for you here.
All right.
For the F# conference. I don't know, we have like 20 seconds for questions.
I think we have probably minus 20 seconds for questions, but that's all right.
Sorry.
There was one question that I was wondering about as well, which is
Right.
not really related to the topic itself, but what does ploe mean?
Oh, yeah. We don't really have time to answer that.
Okay. Well, then we'll have to invite you to the next fsharpConf and have a longer slot for that.
Right, I'll be delighted to come back.
There was one more question which I thought we could answer, which was how do we deal with, for example, string values where only certain values are allowed? So if you want to have a person name where it's only A to Z.
Right. Well, so what you can do is, if all else fails, if you can't design your way out of it, and sometimes you can't, you can configure fscheck in lots of different ways. So you can define custom generators, and then for example, pull from a subset of all possible strings, or you can say, well, you can combine from a subset of all possible characters, or whatever you need to do. And I also on my blog have various examples of how do you generate custom generators. So you can definitely do all sorts of wonderful things with fscheck if you need to do that.
All right. Well, thank you very much for the answer, and thanks for joining us, even though we know it's Friday night.
That was my pleasure.
And we'll be back in a few seconds with a short demo from Krzysztof, who's going to be talking about some of the cross-platform development tools for F#. So see you in a second.